Annotations are not going to work, but that's not going to stop me. This time I need to practice more with this setup. I'll figure it out by the end of the semester. Believe me, this is not my fault. I'm spending endless hours trying to figure out how to make this work like it used to work before this whole thing. All of the news, you have seen this announcement that there is now M1 Ultra. And the thing that was interesting for me, when I looked, when they announced this M1 Max, I stared at this thing at the top and, didn't pay too much attention to what it was. I mean, it looked like some kind of an interface. It didn't look like a memory interface. Was it? I thought maybe it's an HBM interface, but it doesn't look like an HBM interface. What was it? It was the chiplet interface or chip-to-chip interface hiding in the plain sight. So M1 Ultra are essentially two M1 Maxes attached to each other via a silicon interposer. This is a very wide silicon interposer, very wide chip-to-chip interface. Have you guys looked at a little bit at what is in there? I mean, what looks like from people who have analyzed pictures, it is similar to what is Intel's AID, or what we are going to see in technology, what is going to be behind some of these universal chiplet interfaces. It is sitting on an interposer that we don't know what is it made of, but underneath there is a bridge that connects, silicon chip that connects. Why do they do that in silicon? Right, essentially two dies are facing down, they're flipped onto a substrate. And there is this wide chip-to-chip interconnect that is connecting the two of them. They are talking across another little narrow chiplet that is buried into that substrate. So you're going from essentially the way how it looks like. There is one M1 die, there are holes or studs, there is another one, and there is a buried die underneath that is living inside of a substrate. Why do they do this? So any wiring, so there is a transceiver here, transmitter and receiver goes through this. This is completely passive. There is no active circuit in here that we know of, and then it goes into another receiver and a transmitter. That's the same as Intel, how Intel does EMIB. Why do they do this? Because you can get the highest resolution. You get a silicon lithography or a CMOS lithography to work in your favor here, and you can print very dense lines in there. It's unclear that they needed that. I mean, these reverse image reports are pointing to about 1,000 wire interface, running at about a gigabit per second. Similar to what you will find in AID and in interfaces like those. So this is not a 32 or 64-bit gigabit serial interface. It is just a straight wire at about the gigabit and very wide, over 1,000. Wires. We'll see more when this actually gets into people's hands and they start disassembling it. They will burn $5,000 to buy this and then take it apart and tell us all about it. Any other observations from a quiet crowd here? All right. What we did last time, we started using logical effort to analyze the propagation delay of latch. And we found out that flock to queue and data to queue delays are approximately 10 out of 4 inverted delays long when the fan out is approximately 1. That's something that is kind of important to remember. The way how it is split up, and I'm going to have to draw this here. By next time, I'll figure out some of these annotations. The way how it works is, let's say we do C square mass. By the way, last time I brought a whole bunch of these markers. It was on Tuesday. They're all gone. Yeah, the magic of disappearing markers. And we can have inverter and there is some kind of a load at the output. And we said the delay here is 4.9 unit delays, and it is split in the way that we have about 2.7 T unit here and 2.2 T unit here. I would like to find out what is the setup time actually here. What does the setup time mean? It means is the separation between T, D to clock that makes T clock to Q become 5% longer for the purposes of our discussion, which means it makes it grow from 4.9 to 5. You pick a number. 5.2 5.15 T. Okay. What is the growth going to happen? Because the signal here is not going to go, when we are, for example, setting up a 1, it is not going to go all the way down to 0. It is going to get close to 0 in a way that is going to push out this delay by some amount of time. So this delay is going to get roughly 10% longer, 5.25. I made a mistake. So this is 5% is 0.25 approximately of this. So this is 5.15 T, right? So I'm going to get a 0.25 push out. So this is going to become 2.45 T unit. A little bit less, but let's assume it for now. That is the case. So I would like to know then what is the clock to output delay of the CMOS or data to output, sorry. So T propagation for the C square MOS gate that is going to cause this delay to increase. Right, so I can still assume that my data signal is going to sharply rise. There'll be some node, let's call it an S node over here, that in response to that is going to start going down and eventually would go down all the way to 0, but my clock is going to cut it off before it reaches all the way to 0. It's going to cut it off right there, such that the delay of Q delay is, instead of being like that is going to get extended. Okay, so for this to increase by roughly 10%, and this is 10% increase, I would like to know how long does it take for this signal S to go from 0 or from 100% of VDD to 10% of VDD. Does anybody remember those calculations? So I would like to know what is PP of C square MOS from 0 to 90 or from 100 to 10. How many time constants does it take to do that? Oh, actually made a mistake here. We are timing this from 50% here to 10%. So this would be 50 to 10. You can punch this in a calculator. You'll find out that it is equal to about 2.1 RC times time constants. So approximately 3 propagation delays. So what is the propagation delay of C square MOS? Well, we said it is 2.7 unit delays. So that is going to be 3 times 2.7 per unit. What is that? $3.26, 3.7 plus 2, so it is about 8 T units. And that is our setup time. Our setup time is approximately 1.6 and out of 4 delays. And my T clock to Q is approximately 1 and out of 4. So this whole thing is about 2.7 and out of 4 delays. What is the whole time here? And this really approximate calculation. How would I find out what's the whole time? I mean, it happens in time exactly at this, because our calculation is very simplified. You would work it out backwards and find out exactly when that happens. It's about the same as our setup time, right? Just working in the negative direction. That's a simplified calculation that I had here. Moving forward, was this kind of clear? Right, I just, instead of working with full, 50% to 50% delays, I'm looking for a propagation delay from 50% all the way to 90% all the way. You can do this exactly by trying to match the exact increases of propagation delays of each of these gates. But it doesn't make, it doesn't make sense to go through all of that exact effort, because these waveforms very close to VDD are not actually exponential anymore, and our dependence on of propagation delay on VDD is not going to be exactly linear as we go farther from the supply voltage. But it is good for an illustration. It is important to kind of remember these things. Clock to Q delay is about 1/10⁴. Go look in any standard cell library and you'll find out numbers that are basically 10⁴ inverted. The setup times are longer. Longer than 1/10⁴. They'll turn out to be more like 1.4, 1.5. There is stuff that is happening in the design. The other thing to keep in mind is what we're going to talk about in a flip-flop. It is the sum of the setup time and clock to Q delay that is taken out of your effective cycle time. And you'll find out that that window can be moved by placing some kind of inverters into the clock path. But the sum stays the same. And you'll find out, that flip-flops or latches have that setup time plus clock to Q that is about 2.7 10⁴ inverted delays. Let's talk about flip-flops. And I'm going to blast through them by telling you that there are two ways to design a flip-flop. Way one is what we have seen so far. It is to put two latches of that are sensitive to opposite levels of the clock, one after another in a latch pair, and then the other one is to build something that we call the pulse latch. We have seen this before, and I'm going to a little bit emphasize more on that. The point of this slide is that the latch is a soft boundary, and this forgiveness period is something that exists. This forgiveness basically says that my P2Q, which is the overhead of having a latch inside of a data path, is flat during the transparency of a latch. That forgiveness of flip-flop is not really there, unless we really zoom in here and for this really sharp edge, we'll find some narrow here. People who design things that are running at a very high clock frequencies are going to exploit that. We're going to see that in a second. But for now, what would we care about when looking at a flip-flop? You'll find a whole bunch of different performance metrics. People will care about the insertion delay, and insertion delay is the sum of the setup time and clock to output delay. They care about the inherent racing unit. What is the inherent racing unit? Can somebody tell me what is the racing unit of a flip-flop? It's the difference between the clock to output delay and hold time. Which means if I don't have any buffering after the flip-flop, and the flip-flop is abutted to another flip-flop, how much steal before it, I run into hold time violations. That's why most of the library flip-flops have negative hold times, so that we have a good racing unit. It's grad student quote, if you like. And then you're here about the softness, which is what I mentioned before. How soft is this edge? And then inclusion of logic is something that is really important, and how big is the clock load and how constant is its state. Then we care about the power and energy and design robustness. One important feature that we have not addressed before is the testability of all digital systems. And the way how does that works in an RTL design is we have a whole bunch of flip-flops look like this. They're talking through a bubble of logic to another set of flip-flops in our RTL design. So there is a D input to every flop, and there is a Q output for every flop. And there is a clock input. Now there is something that is really, really important when we are manufacturing parts, and we don't do that in research, but every product has to do it. That is something that is called the scan test, or a manufacturing test. When we receive a chip, when somebody receives a chip off a wafer, maybe depending how big is it, somewhere from 50–60% of them are going to be good, up to 98 or 99% of them are going to be good. That means that some number from 50 to 2% is going to be defective, depending how big this thing is and how mature the process is. If you throw away a defective chip right there, the cost is very small. Recycle it. See? If you ship it to a customer, the cost is very high, because you're going to make a product, let's say an iPad, it's going to go to a store, somebody's going to sell it, it's going to go to a customer is going to try to go home, power it up, it's going to crash, it's going to go back to the store, it's going to use the support cycles, eventually it's going to be returned and replaced. Finding a defective chip right out of the fab is like 1,000,000 times cheaper than sending it over to someone else. So how do we find if the chip is broken? It is so-called the scan test, or a manufacturing test that works this way. Each flip-flop has a separate input that is called the scan data input here. And another input that is called the scan enable. I should probably move these over here. Scan data, scan enable. So there is a data input, scan data, scan enable, clock. Data, scan enable, clock. And that's what we have everywhere. What will be done here is this. Our output will be connected to a regular logic, but perhaps that same output, or there may be optionally another one, SQ output. It depends on the convenience. Most conveniently, usually it will be an SQ output, separate one, such that we don't have to deal with this load accounting. Would be connected to scan data, and this will be connected to scan data, and so on. They'll be chained into these strings that will be used for test purposes. So how does this work? When the chip is for the first time powered up, what we do is, on the clock input, we will configure it to work as a very long shift register, and we'll shift in 1,000,000 or 100,000 or 10,000 or whatever long value into the first stage of a pipeline. Our scan enable signal will be high. And we'll drop our scan enable signal to low. I'll clock it for one clock period and scan out the value. What is this going to do? We will, if we have just a 4-bit long scan here, we would scan in a value here, clock it through the logic for one cycle, and scan it out. We would, outside of the chip, in a tester, we would compare the value that we got out from here from what we believe we should have gotten if this chip was working correctly. If it is all good for all the flip-flops that we have in a design, the chip is good and can ship. Probability that something escapes the scan test is very low if it is designed well. Essentially, the tools nowadays and the understanding of logic design basically makes it, test escape loss is negligible. Yes.
Checking the first stage of the pipeline using this scan tester. Are we also, data is propagated to the second stage and third stage and vice versa later?
Exactly. So this is all strung into these tens of thousands long strings. So you load them up, clock for one cycle, scan out, load again, clock for one cycle, scan. And with a finite number of test vectors, you can check the entire chip. You can have 100% test coverage. Okay, what does that mean? That every flip-flop has to have this feature enabled inside. What does that feature mean? What is that logically? If you're designing a flip-flop, there is a flip-flop core inside, there is a mux in front of it. And there is your scan enable signal that basically goes into the data, and here is your regular waterfall. And this Q output may have another version over here that is SQ. Right. So this would be your other output that just gets connected during the scan. Is it clear how it works? So every flip-flop has to have this, right? I mean, you can play in, with the research chips. We don't do these kind of things, but anything that is in production will have to have these features, which means that every flip-flop has to have this ability to cheaply implement a multiplexer in fact. There is another way of doing this testability by using two different clocks, but that is less dominant now. So two separate clocks, still two different inputs for scan in and scan out. What is the danger of scan here? I mean, this is by default creating, near race conditions. So that's why on purpose I've shown here that they do build in a load, they make this scan path a little bit slower. You don't want to pad it too much because it burns power unnecessarily or bloats and so on. That's why you want to separate the two outputs, because in normal operation, these are not going to be clocked. These are not going to be switching. So you want them out of the way there. And you don't want to slow down unnecessarily the regular path. Does this make sense? Everybody understands the nature? My internet connection is unstable, great. So, two types of flip-flops. A latch pair and a pulse trigger latch, or so-called British latch. Latch pair is simply a pair of latches that are transparent on opposite faces of the clock. If I have a transparent high, transparent low latch, followed by a transparent high latch. What kind of a flip-flop do I get? Clocked on a rising or on a falling edge of a clock? It's on the rising edge of a clock because essentially the data would go through when clock is low, stop here, and it would transfer the output of the second latch on the rising edge of a clock. It never goes through. If I change the order of these two, I end up with a falling edge. This thing here, the other option, the other construction of flip-flop, this is designed, the first page is a glitch generator that makes this transparent high latch transparent only for a short amount of time, and it makes it look like a rising edge sensitive flip-flop. Let's quickly figure out what is the clock to Q delay and what is the setup time, and also the whole time of a flip-flop here. Take a look at it, and can somebody tell me what is the propagation delay of the building blocks inside of this flip-flop that is going to, they're going to account for the clock to output delay? So what is the clock to output delay? That is the delay. The data is going to propagate for the flip-flop up to some point, and then it's going to, on the rising edge of a clock, just proceed. You can ignore these things for now. I mean, this is a side load, it's all way smaller, and we know how to add to it. So what is roughly clock to Q delay of this flip-flop? I mean, this is a library flip-flop design. This is a transparent low latch, transparent high latch, middle inverter is shared. Any suggestions? So when clock is low, the data is going to propagate through here and through there and sit at this node. Wait for the clock to rise. If clock instantaneously rises, clock to output delay is the propagation delay from this point. Yeah. What is that? It's the delay of a transmission gate or a C-square MOX, because these two things are identical, plus one more inverter delays. This second inverter is kind of optional, but we'll find it over there. In essence, this clock to output delay is exactly the same as what we have had in case of a latch. There is no difference. The latch would have that optional inverter in the output as well. So there is no difference. What's happening? How about the setup time? What is the setup time here? So it's the time for this input to set up such that this value is within 10% of the rail. compared to a latch, what can you tell me about this? In a latch, it basically had that propagation delay from 50 to 10%, or 50 to 90% for a C-square MOS. I here have a C-square MOS plus an inverter, always. It is a little bit longer. So the setup or flip-flop is a little bit longer than the setup for a latch. If I ask you to do this, would you be able to do it, to do the calculation? I'm sure you would. So that basically gives us a somewhat quantitative evaluation, why flip-flop is a little bit longer, is a little bit slower, because the sum of setup time plus clock to output delay is longer by about 1 inverter delay. Roughly 10 out of 1 inverter delay. And that's because clock to output delay is about the same, but setup time is extended because we have more stuff. Now, one thing to keep in mind here is I can move that. I can trade off a clock to Q delay for setup time. We put more inverters here or less. So it just basically changes the, exchanges the setup time for clock to Q delay. Now, in early 90s, there was a rash of papers in respectable conferences and journals where people were inventing new flip-flops that had really low clock to output delays. You know what they did? They made some complicated circuitry. It essentially made clock to Q delay be 0, but pushed everything over to the setup. So they had very long setup times. I could do that and make perhaps even a better flip-flop by simply sticking an inverter. Until people realize, oh, what they're doing is they're just exchanging setup time for the clock to Q delay. Gain nothing. The way how we time flip-flop clock to output delays and setup times is again by using two-dimensional tables. Clock to output delay is a function of the output load and clock rise. That is, again, very similar to what we had in combinational logic, where our delay was characterized as a two-dimensional function of the output load and the input rise time or hold time. Setup and hold times are functions of the slopes of the data and clock. So there are, again, two-dimensional tables that are functions of rise or hold times of data and clock, not the function of the output. If you look at the structure of a flip-flop, you'll find out that they're geographically separated from each other. So input slopes govern the setup time, the clock to Q governs the output propagation delay. Keep that in mind, yes.
Explain how the rise time is relevant to the input is rising slower or faster.
Okay. So how is the propagation delay dependent on the clock rise or fall time? Well, remember it's the same story as that we had as in a latch. In a latch, we had a situation where we thank you for finally asking some questions. So here is this node, we'll call it an S node. Again, this is Q, this is D. I have essentially my clock my say data goes from 0 to VDD. The S node goes down from 0 from VDD to 0, and my Q goes in response to the clock. So this will be key today. I need to add the clock to it. What did I do with it? Where do we want to put the clock? So to make this transparent, the clock would go here. So it is non-transparent and becomes transparent. My S node is going to follow this, and my D to Q is gonna go down. If I change the slope of the clock, that is going to extend my Q. Simply, it's like combinational logic delay. Similarly, you can draw this for the setup time side, and you find out that it is only the slopes of the data and the clock that affect the setup and hold times. Now, there is a major caveat over there, because it is very sensitive to the clock slope. This is a most common error that we have had in among analog circuit designers. They, at the very end, they will put their control bits onto a scan chain. And then they will be fairly sloppy by inserting in the way how they insert the clock. So the clock will have the clock that they use for controlling the scan chain that goes around the chip will have a bad slope. What would that mean to the hold time? Would shift the hold time out and make essentially create a race condition between the clock and the data. As a result, the scan chain will fail here and there and would cause a lot of tears when after that is realized. So keep this in mind. Your hold time is a strong function of the slopes. The way where you can mess up the slopes is by not having a good clock or not sharp clock whenever you're designing your test chip. Analog people, any analog people over here? I don't want to see this happen, 2 years from today. Okay, we talked about this. Let's talk a little bit about these pulse triggered latches. I've shown them before. The first stage is a pulse generator that makes a glitch, and the second stage is a latch. In the way how it works, if you plot it this way, it naturally creates a system that has a negative setup time. So you have a latch that is transparent, and here's your glitch generator that makes that. So in timing sense, here is a latch that has this is going into a latch. The data can totally change here legitimately and go high or low, while the latch is transparent. By definition, it has to meet a setup time. Latch is setup time on the polling edge of the clock. As a box, we are timing this as a rising edge flip-flop. So this would be a rising edge flip-flop. There is no bubble here. So we are timing it with respect to the rising edge of the clock, but the inherent mechanism inside, the internal mechanism, latches on the falling edge of the clock, which means that my data can change after the rising edge of the clock. And inherently, this thing has a negative setup time. What does that mean for the clock to output delay? It is often longer than what we have encountered before in two-stage latch pairs. What does that mean for the whole time? What is the whole time happening? This needs to be stable out there. The whole time is very long in pulse triggered latches. Frequently longer than clock off. What does that mean? This is a terrible choice for your scan chains or something like that. The reason why people design this kind of a thing is because the sum of setup plus clock output delay is shorter than for a latch pair. But at the expense of long hold time and the danger of having race conditions. Keep in mind that this glitch generator burns power every time a clock edge arrives. And it is a dominant source of power dissipation here. So these things are hungrier than latch pairs. Often, what you will find out now is that a pulse generator is shared by a register. There is one for a group of 8, 16, or more often. Okay, the first design here that I'm aware of in the literature comes from Kozu in ISSC 1996. Can you help me decipher what is in this picture? Well, it's a two-stage design. There is a complicated circuit and a simple circuit. What's in this simple circuit? A pass transmission gate and an inverter. Oh, jam inverter with a tri-state. This bubble here basically means this is C-square mass. So transmission gate C-square mass is a feedback. Yeah. Transmission gate and a feed for C-square mass. The feedback designer's choice. We could have done it in any other way. Transmission gate C-square mass, C-square mass, C-square mass. All right. So this is my latch that is transparent high block. I'm actually show a non-bubble. What is this thing? Well, it is something, if you look at it, that on the rising edge of this yellow KI goes through an AND and 3 inverters. So essentially a positive kind of feedback. It goes back and shuts off this AND. So there is a pulse, this clock, after some propagation delay, goes high and then goes low after approximately 3 inverter delays and an AND. So as a result, it generates a pulse. And they generate both tri-componentary phases. It's a pulse that has a width of 4 gate delays, 3 inverters, and an AND. Well, that's the simplest idea that we have seen so far. Transparent gate, transmission gate-based latch and a pulse generator. It has a beautiful negative setup time and horrendous hold time. Okay, can you do better than this? yeah, you can come up with better and better control pulse generators. And this is what was done in Intel Titanium in early 2000s. There is a latch here. It's right there. So transmission gate and an inverter. They're not showing this data, but there has to be an inverter. Otherwise, they have to very carefully time it because this delay is going to depend on the gate that is sliding. They have to have this whole thing in order to implement the scan. The other chip that I've shown from 1996 was a research chip, so they going like the low that kind of stuff. Scan and so on. All this is the product. So it had a scan input and a glitch generator. This glitch generator, what can you tell me about it? There is an enable here because they would like to gauge it at a fine granularity. They don't want to burn too much power if they don't have to. So there is an enable symbol, enable input for gauging it at the lead. How does this work? How does this thing make a pulse? Well, it's essentially a two-input NAND gate. This is like a degenerated NAND gate that makes a pulse and shuts it off after one inverter delay. See, here it has a stack of two inputs. One of them is true, the other one is complementary. It's just a single inverter. There are a few other interesting designs out there. This is a dynamic stage. The second one, this is hybrid latch flip-flop by AMD K6, mid-90s. Type of version re-emerged a few times afterwards. Most recently, I think, in a few of production chips in different versions of that. Input NAND, clock, and data, pulse generated by three inverters, and then there is a dynamic latch. And I have not covered dynamic latches, but there's a dynamic latch as well. We can figure out how does this work. It's essentially a pre-charged semi-transparent latch. A little bit, this is out of favor these days. We are not allowed to have dynamic circuits anymore. And this is showing back then characterization where it was clearly showing that it has a negative setup time of 9 seconds back in that technology. And this is again showing why it was called a hybrid latch flip-flop is because it's an edge triggered flip-flop, but it has this nice property that it is transparent for the duration of 3 inverter delays, which means, remember my, the softness property, is able to absorb the skew and local jitter during those 3 inverter delay, that 3 inverter delay period, and essentially be forgiven. So this is what we're showing, that there is some sensitivity on the rising edge of the queue, no sensitivity on the falling edge of the queue or the dynamic latch with respect to the change of the arrival of a clock by approximately 150 seconds. This is a big deal back then. Remember, this was late 90s. This was the race for clock frequencies, and that was the other time in history when AMD was beating Intel. And a lot of that was attributed to their clocking and latching methodology. Okay. A completely different structure is this one. This is probably the first flip-flop that was out there, designed in like 60s, maybe early 70s by TI. It consisted, again, of two stages. The first stage is a pulse generator. The second stage is an SR latch. Anybody has heard of an SR latch, set reset latch? It's just, it's an ancient history. All of our latches are B types now, but there is a way, there is a different type of a latch topology that is shown over here. If I go and cross-couple two NAND gates like this, if I yank this signal as low, and I could do this with OR gates and have a positive logic, this would set the flip-flop to output Q would become high. So I would keep the reset signal high. If I do the opposite, if I yank the reset low and keep the set signal high, it would reset the flip-flop. So what does the pulse generator do here? If data is high on a rising edge of a clock, it should make a negative pulse on S and keep our bar steady. If data is low on a rising edge of a clock, it should make a negative pulse on the reset to keep set steady. That's it. That's all what is about that. Now, this fell out of favor because this thing is really slow. Remember what we had before? We had a 10 out of 4 plus something, 1.5-ish 10 out of 4 for the second time. I mean, this thing goes on and on. Through NAND gates. So this is really slow. But there was a time of, my parents, your grandparents or so, they didn't know better back then. This got reinvented in mid-90s or early 90s. And first they started working on the pulse generator. Instead of having a whole bunch of NAND gates, there is a different way how you can generate a pulse. People have seen, oh, this looks like a sense amp in memories. And that's what they went with. This is a sense amplifier, probably one of the more dominant memory sense amplifiers nowadays, invented back then, where you have this structure here. There's a dip there, there's a clock on the bottom, and a cross-coupled kind of an inverted very low output. When clock is low, this thing recharges, and all these signals are at VDD. When the clock edge rises, the dip there compares the values that it sees at the D and D bar inputs. And essentially will yank one of these sides low, keep the other one high. So if D is equal to 1, this side is going to go low. It'll create a pulse over here. We'll call that pulse a set bar. This one's going to stay steady at D, and you're going to latch that the cross-coupled inverter. Okay. Yes.
Why do you have the N5 MOSFET between the two?
Why is this one? This is an interesting one. This is to prevent dynamic state over here. So the side that gets yanked low, this is like a resistor, and there are better ways to implement this. Here's what happens. This node gets yanked low, stays low. This one is dynamically how high. It can happen that if you disable this, if there is some kind of enable signal, you can keep it in that state and flip the inputs, the bar. Just invert those two. And the output will change. We don't want to allow for that, so what they want is they make sure that this thing also discharges, but after the other edge, so it will not be affected by the changes of the data. And there is a better implementation of that. Shown over here, these high Z inputs make sure instead of having that resistor across, they put the other resistors to this. What's the problem with this implementation? Still, my clock to Q delays essentially goes through two NANDs instead of being one fan out the core. So it is something that corresponds to discharging this like a 3-input NAND and 2 more NANDs. That's slow, even though the setup time is 0. So you can speed that up, but instead of using cross-coupled NAND gates, you use cross-coupled inverters, and then just on the side, you design this network that yanks the side of those cross-coupled inverters towards VDD and ground. So essentially, what we see here in the situation is that one of these are going to be pulling low, the other one is going to be pulling high on a set side, and the opposite way on a reset side. Propagation delay much shorter. So what's the best way of designing a fast flip-flop of all the pulse latches? Well, here are the 3 designs that you have here. This is showing clock to data separation. This is latch overhead, flip-flop overhead, the Q delay. So as we have seen, remember that plot over here, we see a linear decrease as data gets closer to the clock and then runs into a setup time. And there is a different amount of forgiveness between the 3 designs. Now, this was published in a paper where IBM was trying to, where Intel, HP were trying to highlight why they have the best one. So theirs came down as the shortest, the lowest overhead on the bottom. So that's the pulse generator plus the transmission group. Now, if you zoom in into this, the differences between the 3 are really small. So this is the HL effect, and this is a sensor flip-flop. Differences of time. However, this programmable width of the forgiveness is an attractive feature for people who design clock networks and worry about the timing of things that need to run really fast. Does this make sense? Essentially, I mean, when you look at them, when you do the analysis like I've done of each one of these, you're going to come up with about the same delays. Something that looks like a NAND gate followed by another, say, NAND gate in logical effort terms. And not much more than that. Now, the devil is in the details of what that boils down to. But they're about the same, different kinds of realizations getting to that minimum possible delay, and different preferences of designers. That wraps up latches and flip-flops. A few announcements. We have a lab that is due this week. We do want your midterm reports due next week, and we would like all of you to discuss with us anything
related to your work. Remember, it is 4 pages conference format, meaningful. And we're going to post another assignment this week. It'll be due right after the spring break. Any questions? Yes.
When did we get our feedback for the?
You were supposed to get it, so no. Okay. We divided it up between the 3 of us, and hopefully we'll get it now. I don't know, somebody, or unless we lost your proposal. Okay. Bug us about that. The next topic that I would like to address very quickly, and it will spill over into the next lecture, is the impact of variability, process variability on the design. And it will yield, go into this, why do we design memories in a particular way? The process varies. I mean, there is a very simple thing. There are no 2 identical transistors in the world. Maybe you will find them somewhere over there, but there are so many transistors out there. You can just look at these things that have, one of these M1 Ultras has 112 billion or something like that. Every cell phone has billions of transistors, and yet it'll be pretty hard to find one that is absolutely atomically identical to another one. The way how we can classify these variabilities are in different ways. In general, what we care about is understanding the nature of variability. Why? Because if we understand it, we can account for it. If we don't understand it, we have to worst case it. There is a simple thing that happens there is if things are random and uncorrelated, we treat them differently than random and correlated, and yet we treat them differently if they're systematic. So the way how we're going to deal with that, we're going to look at the nature of process variability, how things vary within the die, die to die, the device to device, how things vary in space, and how they vary in time. Sources of variability could be technology, basically systematic and random variations in ion, IOP, and capacitances of front-end devices, and in the back-end, interconnect varies. And then the environment, deployed environment varies. The things need to work the same way, whether they are operating in, I don't know, in the north of Canada or in winter or in Africa in midsummer. So we care about the temperature, but we also care about supply variations, whether they're locally done or globally because of the battery wear out. There are many things that on the other hand, you as a designer, you don't know what are you doing, what is going to happen with your design. You need to anticipate this. So it will happen that there will be a variation from a path to a path. If you're designing something that is in a really big success, a big hit, it's going to be made by multiple paths. Those 2 paths may not be identical, and maybe actually on different continents. Your design has to be sensitive to that or understand some of those things. It will depend. So this can be a different continent. If playing the environment can also be on different continents. Then when you are looking at a smaller scale, it can vary from a lot to a lot. Again, you may be designing something really high value, and all what you're going to have are a couple of lots, or you may be keeping a fab busy for 6 months if you're super successful and you work for Apple. Things are going to change as they come out with the fab over that time. And then things vary across the way for across reticle, across chip. Then you have these things like local variability, related to temperature. Things are going to be correlated within within a chip because the temperature does not heat up everything equally. Metal polishing, resistor ion, lineage roughness, down to fluctuations of dopants that affect the devices, or film thicknesses inside of a device. Or things may vary in time. There are things that will happen, especially if you're in a leading node. You start making something and the fab changes the process underneath you, which is a fun thing when you're designing something. So your design has to be sensitive to that, as well as being sensitive to all kinds of other things. Within node scaling, they may change the equipment along the way. Electromigration, negative bias threshold instability, carrier effects, and stuff like that. And then in the environment, things may change in time. Your phone may be working here, and then you take it outside. The temperature, environmental temperature, will change. Data stream, history effects, self-heating, and so on. A big thing here is understanding what is systematic, what is truly random, and what is unknown. So if there is a systematic pattern that can be traced to something, it's important to know that, because we can account for it in the design. If it is unknown, we need to treat it that way. But there is a big difference between the things that are correlated versus uncorrelated. And there are certain things that you can do with those. Now, there is a really important thing. In general, anything can be attributed, any variability can be attributed to a source. And there are no things that are, there is nothing that is truly random. I mean, very few things that are truly random that we have to account for the design. And there is a good illustration of that about, what is the most commonly accepted, random process in public? What do they use to determine, I don't know, in football games, Super Bowls or whatever, there is a big ceremony, there is a random event that is happening up front on who gets the ball or whatever, who gets the kickoff. There's a coin toss, right? Coin toss is the most widely accepted random event. It's not random, what is random about it? We know the weight, we know the height. The only thing that we don't know is the initial force of the coin flip. I mean, if we can just snap that, we can calculate and figure out exactly whether it's going to fall heads or tails. There's a paper published about that. I mean, what kind of a speed, camera speed and processing you need to figure out, whether it's going to come down heads and tails. Now, that's exactly what is happening in design. We can try to attribute for some things, but some things we just don't have time to account for because they may happen before the coin. They're going to happen. Our reaction is going to happen after the coin falls in the ground. All right. So here are some of the systematic and random effects. There can be many more of them. I will briefly go through them. They involve a bit of device physics. But essentially, dopants inside of a channel. Most channels nowadays are doped. How many dopant atoms? First, why do we dope channels? Increased motility could be, or generally we do it to adjust the threshold. So systematically we'll vary to adjust the threshold, but randomly the number of dopant atoms is going to vary. How many dopant atoms are in the channel or in the thing? Anybody has any idea? Numbers are really intense to maybe hundreds. So it's a random process. I mean, two transistors, one may have 95, the other one may have 85. go for patterns. There'll be a random threshold variation. Same things apply to gate oxide thickness. That is usually a reasonably controlled process, but there may be, the standard, systematic variations are small, but it may vary around layers. Threshold voltage may vary based on the environment, and it will definitely vary because of the strain that is applied to it. In general, that is something that is systematic, but may not be modeled, and you may not be extracting every single one from every resistance environment, and there may be a random strain of variations. Mobility, again, tends to vary because of the strain. Gate length can vary systematically because of the lithography, and also of the overall gate density around it. There is a random thing with this whole line and sharpness that is something that we need to be aware of. And then there can be things that are associated that how the fins vary. What happens if you discover, related to this, how quickly can you figure out how random is the coin toss? What happens when you find a systematic cause of a systematic effect that is affecting a design? You generally have three options here. Try to tell TSMC to improve the process. Good luck with that. I mean, unless you're like Apple or somebody like that. So okay to go tell TSMC to fix their process because you found out something that you don't like. It's likely not going to happen. You can try to tighten the design rule, and you'll find out that there are some companies that will use this generic design rule, and then there is a production design rule, but you're not allowed to do so. That is a totally, they require double contacts. You may be able to get the chip back with a single contact, but your company will require double contacts. And they will impose that rule additional code to you. There will be typically some density losses associated with many of those additional manufacturing codes. Or you can try to model something or design it. So that is, these two options. So understand that something is happening, you build a model for it. It is a plot of a coin toss kind of a thing. This is showing, and this is amazing how they published it. This was IBM's fab. Metal-free resistance over 3 months measured across scribe lines. So, every wafer has scribe lines that you use to extract the chips from. And this is showing how within the day it changes as they're measuring every single one of the wafers, and then what it does over the 90 days. As you can see on the average, so this is supposed to be the low resistance is supposed to be the fast corner, slow corner. But it is on the average over 3 months is running closer to slow. And it goes out to specs for a moment. Somebody comes in, probably shuts it down and services the machine after they observe something like this. This may not mean that all the chips have failed here, but there may be more of a yield loss on that particular day or those two particular days. Can you account for this in the design that on the average metal tree is going to have a higher resistance, or that you're going to have a yield loss in 7 to 9 days into production? No. There are systematic effects that are just going to happen. But if there is something that persists over time and can be characterized, you can design for that and adjust your models. We'll pause here, and we're going to talk about how we treat this. We'll spend about 20-ish minutes in the next lecture. Maybe someone else will do it, maybe Vladimir, and then we will move into a memory, which is an example of variation tolerant design. All right.
Stop by for any feedback that you would like about the projects, whether you got it from me or from someone else.